So today I'll be telling you about the evolution from starburst to post-starburst. Yeah, so post-starburst offer a unique view into galaxy evolution because they are believed to be recently quenched galaxies moving from blue cloud to red sequence. We believe maybe they might have some quenching signature imprinted into their unique spectral features and structural features. So here in the image, I'm showing you the image of post-starburst. As you can see, it has prominent bulge. It's greenish, and in its spectra, the features you see are it has no emission lines, indicative of current star formation, but it has spectral features that show strong A-star population in the H delta, H delta, and the Balmer absorption lines. So that's why we think these objects are recently quenched, because they don't have current star formation but had experienced recent star formation in recent past. So in post-starburst, quenched post-starburst are believed to be merger. They are believed to be aftermath of gas-rich mergers, where in gas-rich merger, gas is funneled to the center due to tidal torque, and that powers compact starburst, and then most of the gas is consumed in the starburst, and then the remaining gas and dust is removed by feedback due to stellar feedback or AGN feedback, and then in the end we observe quenched post-starburst. So here do I have? Pointer?
It should be on the dam, right? To your right.
So here I'm showing a simulation from Snyder 2011. So where he compared how the Balmer features depend whether due to the presence of AGN or its absence. Basically what he finds is overall the Balmer features are not affected, the star formation rate are not that affected by AGN, except that AGN seems to lead to enhancement in Balmer features by removing gas and dust. So our task is to follow every evolutional step from starburst to post-starburst, and this is not easy because post-starbursts first are rare. They are less than 1% of all galaxies, and they evolve across regions that are they pass across normal galaxies. And then there is also bias because usually post-starbursts are defined by lack of emission lines, but those, for instance, H alpha can come from AGN or starburst. If you have a quenched post-starburst, but its emission line is coming from AGN, by traditional selection of post-starburst, you will be biased against that. And there is also incompleteness of selecting AGN. For instance, if you have measuring the Balmer absorption lines is hard for strongly emission line dominated system, because you have to correctly correct for emission infill, and also dust complicates the identification of post-starburst. So here I started with a sample of parent sample of object drawn from the Sloan, and then I matched Sloan with WISE and Galax, and then I want to study post-starburst starburst to post-starburst evolution in a small slice, because if the starburst to post-starburst evolution is merger-driven, the maximum mass increment I get is a factor of 2 due to two galaxies merging, and the amount of stars formed in a new burst is less than 20%. So I will not experience more than 0.4 DEC increase in mass when I evolve from starburst to post-starburst. So I made a volume limited sample, and in a mass range between 10.5 and 10.7, which is a transition mass where a lot of galaxies are currently observed to move from blue cloud to red sequence. And then I make that's a redshift cut. I'm only looking at object redshift above 0.05 to minimize for fiber effect. And then I also looked for object face on to minimize the effect of dust obscuration due to inclination. And then I looked at, I also selected only objects that have high signal to noise ratio in their spectra, because I'm going to use these spectral indices to identify post-starburst. And then I only looked at objects that have continuum H-alpha flux, because there may be gap in the spectra around H-alpha, so some objects may be misclassified as post-starburst. And I do dust correction on the colors using Charlotte and Fall model, and then I adopt empirical dust correction from Wild 2011, and then I also use the ratio of tau between stars and gas from Wild from Wild 2011, and I also do dust correction, K correction following Blanton 2005. So first, I define starburst. Starbursts are traditionally defined in many ways. The one I adopted here is starbursts have the ratio of their current star formation to the past star formation above 3, which this is quantified using the H-alpha equivalent width. So H-alpha equivalent width usually above 100 before the dust correction corresponds to the birth rate of 2 to 3. So if I do the dust correction, and then of course if we for instance assume the gas is extincted twice than the stars, following Calzetti, 100 corresponds to 160 after dust correction. And then the typical star formation rate in the starburst is around 10 compared to 1 in normal galaxies. So that gives me the definition of post-starburst. And then I define quenched post-starburst, shown in red. They don't have any, they have weak or no emission lines in H-alpha, but they have strong Balmer absorption lines indicative of recent star formation. So, and then my aim is to go from starburst to post-starburst and identify objects that are transiting between these two phases. And then the way I select them is I select post-starburst, transiting post-starburst, if there are 3 sigma outliers from normal galaxies. Here I'm showing D4000 H delta, and object forming object in the continuous star formation lie in this region. So there is a best fit line shown in magenta. So any object that deviates from this best fit line at 3 sigma and also deviate from in NUV minus G, dust corrected, and D4000, I select. So combining these two plots, I select the transiting post-starburst galaxies. So those are shown in green here. So the difference between this diagram in the first one is basically I replaced H-alpha by NUV minus color, because H-alpha may be contaminated by AGN. So that gives me the green object. And then next I select obscured post-starburst, because in the previous selection I had to correctly correct for the emission infill but that may result in problem for extremely dust obscured object, because we have to correctly fit the continuum and then subtract the emission line. So here to select the dust obscured galaxies, I use the ratio of NUV to mid infrared as indication of obscured star formation rate. And then here I'm going to use a ratio of 4.6 to 3.4 as indicator of hot dust. So when you look at this diagram, most 50% of starburst are significantly dust obscured, and quenched post-starburst are not so dust obscured. Transiting post-starburst are relatively dust obscured. So I'm wondering if I could miss this obscured object with post-starburst signature and dust obscured signatures. So I select the red crosses from this diagram, and I test whether these are a good candidate for post-starburst that I missed in the first selection. So if I plot them in NUV minus G, color versus D4000 that I used to select the green point in the previous diagram. So here I can see actually the obscured post-starburst and the transiting post-starburst have the same the spectral property, the same age and the same color. Probably the reason why I missed the green point, the brown crosses, is because their H delta is not well measured, probably due to emission infill. So I have 4 samples, and then I test the prevalence of AGN in the post-starburst. So I'm showing BPT diagram. So here is a Keeley line of maximum starburst, and as you can see, quenched post-starburst are mostly AGN dominated, but and then starburst, as you expect them, are below this line mostly. So the transition post-starburst and the quenched post-starburst nicely bridge the two population. Usually, to classify object in AGN in the BPT diagram, you require well detection of the 4 lines. So the simpler version of BPT that Ted Fernandez has developed is the 1 diagram. In the 1 diagram, using a 1 diagram, so I find that 40% of post-starburst are AGN dominated compared to 20% of normal galaxies. And then I compute the time delay between starburst and post-starburst, the ones that are. So I want to know when the appearance of AGN. So here I took the median composite spectra of starburst here, composite post-starburst and AGN obscured post-starburst, and then these are AGN transiting post-starburst. So what I find is AGN is significantly delayed from the peak of starburst, and then I also investigate whether whether quenching is, if there is any relation, structural relation between post-starburst and starburst, and if that signature is different from normal galaxies. And I find starbursts are mostly merger dominated, 17% compared to 3% of normal star-forming galaxies. And then the merger signatures decline from starburst to post-starburst. And then I find that the starburst and post-starburst are small and compact. And then here is my conclusion. So my conclusion is we try to identify the post-starburst to starburst, the starburst to post-starburst evolution. In this evolution, we find that fast quenching makes more compact object, and then the appearance of AGN is delayed by about 200 mega years from the peak of starburst, even though AGN are more common in post-starburst galaxies than in normal galaxies. Consistent with merger hypothesis, we found that starburst exhibit clear merger signatures, but these merger signatures disappear from post-starburst, from starburst to post-starburst phase. But both post-starburst and starburst have prominent bulges, and then we find that the starburst, the evolution, as starburst evolves to quench post-starburst, they pass through heavily dust obscured phase, and then AGN may be related to clearing dust in post-starburst galaxies.
Take a couple of questions. Original ones. Joe? Yeah.
You talk about indications of mergers, especially in the post-starburst, not in later. And I wondered what those indications are. If they were, for example, tidal tails, that's an indication that it's a real wet merger of disk galaxies. But if it's just asymmetry, that could be disk instability.
So first, the first indication is compared to normal galaxies, post-starburst are classified as merger remnant by Galaxy Zoo. That's one signature.
Based on what? What are they looking at in order to classify?
They just look at the image and then whether it looks merger or not. That's one classification. This is just visual classification. The other merger signature I presented is if you look at the smoothness parameter, which is a combination of clumpiness versus plus asymmetry, or it could be both or either. We show that 50% of starburst are asymmetric or clumpy compared to normal galaxies, which is 30%. So clumpiness or asymmetry is the...
So clumpiness and asymmetry could be not merger, but disk instability. On the other hand, tidal tails are certainly merger. Makes a big difference.
Some, for instance, in the example of starburst, I showed when I defined starburst, you can actually see a tidal tail in that object. So, but since we are using Sloan, you can see that they are disturbed, but it's hard to see to look for clear merger signature. But high resolution studies of post-starburst, the ones that come much later, even show people find actually disturbances and tidal tails in these systems.